Hello again, physics friends. Here we have a very brief video doing a couple examples for a given force, looking at the curl of that force and determining if the force is conservative or not. And as you remember, there's two conditions that have to be satisfied for a force to be conservative. Number one, that force can only depend on the position, not on time or velocity or other factors. And number two, that the work done by that force must be path independent. And we later learned that the curl of the force equaling 0 ensures that the work done by that force is path independent. So let's make sure that we understand how to actually do this in practice. So let's consider the following force. We'll have two examples here. Here's our first example. Example 1, we'll take as our force the function y0. And we've seen this before, right? That force looks like the following. It has force vectors that grow as you move up the y-axis, and those force vectors point to the right. Also, as you go below the y-axis, you have an increasing magnitude of force, and they point to the left because now you're in negative y territory. And if you are on the x-axis, you're at y equals 0, there's no force to speak of at that height. Okay, so number one, we've already seen scenarios where the work was path dependent. So we already found that the work was path dependent in the previous example when we took different paths from one point to another point. Okay. In particular, if you march along the x-axis and then up, there's no work done because all along the first stretch there's 0 force, and all along the second stretch there is a force that's perpendicular to your displacement, so no work done. Alternatively though, if you go first up and over, now there's no work going up because your displacement is perpendicular to the force, but as you go over there is work done because your force dotted into your displacement is non-zero. Okay, but here we just want to show mathematically that indeed the curl must be non-zero, so we expect here the curl of this force to be non-zero. Let's just check that that is in fact true. So we want to here take the curl of this force. We already have shown in previous videos a way to do the cross product rather between two vectors, and here we're going to treat this as the determinant of a 3x3 matrix, where the first row are the unit vectors. The second row are the components of the first vector in the cross product. So we're going to think of this del operator as a vector that's ddx, ddy, and ddz, where each one of those is a partial derivative with respect to one of those coordinates. So that will be our second row. And then the third row here is our force vector, which has an x component of y, a y component of 0, and a z component of 0. And just a refresher, the way that I like to do this, you might have your own technique for doing the cross product, but the way I do this visually is by recopying the first two columns and then multiplying diagonally like this, and that those red lines correspond to positive quantities in the product, going this way to give me negative quantities, and stitching it all together. So looking at the positive quantities, I have ddy of 0 in the x-hat direction, so that's 0, plus ddz of y in the y-hat direction, and that's also 0, because the derivative of y with respect to z is 0. And then in the third, I have ddx of 0 in the z-hat direction, so that gives me 0 again. Then I look at these blue lines, and going along the blue lines, each of those terms contributes with a minus sign. So then I have minus ddy of y in the z-hat direction, which is going to be non-zero. And then I have two terms which are both 0, because it's ddz of 0, ddx of 0. So when all is said and done, this curl ends up being minus 1 in the z-hat direction, or equivalently, I can write this as 0, 0, minus 1. That is definitely non-zero. Therefore, F is not a conservative force. Okay. So I just wanted to give you a flavor for how you would actually do an explicit calculation using the curl of a force to show whether or not a force is conservative, at least for one of the criteria for that force to be conservative, the other being that the force has to be independent, dependent only on position and not on time or velocity or other quantities. Well, let's do one more example. In this example, our force will be equal to minus kr. This is our 3D spring. And the r vector can be written in Cartesian coordinates as the x, y, and z, or x in the x direction, y in the y direction, z in the z direction. That is the position vector in Cartesian coordinates. And we identified this as a three-dimensional harmonic oscillator. So this is like a mass on a spring where the spring essentially has zero rest length and one end is fixed at the origin. And no matter what direction you pull the spring, there's a restoring force back to the origin. So we also drew kind of a sketch of what the force vectors here look like. All the forces point radially inwards. And the further you are from the origin, the longer those force vectors get. And here I'm just drawing it in 2 dimensions, but really this is a 3-dimensional force field. Okay, so maybe this is the x and y dimensions. It could be any pair, actually. Okay, so what we found for the paths that we had considered was that the work seemed to be path independent, but we only considered 3 different paths. And here we want to see, in fact, we want to show that the curl of this force is in fact 0. That coupled with the fact that the force depends only on position that tells us that this force F is conservative. Okay, so let's actually do the curl part now. Right, it's the same deal as before. We'll look at the determinant of, we'll look at the cross product, which we can think of as the determinant of this matrix. First row, unit vectors, second row, first vector in the cross product, third row, the force. Okay. And I copy out each of these terms in the first 2 columns one more time. And I do multiplication along the diagonals. And when this plays out, I'll look at each of these derivatives, d dy of z, d dz of x, d dx of y, d dy of x, d dz of y, d dx of z, d dy of x. In each of those cases, you're taking a partial derivative of one direction, of one coordinate with respect to a different coordinate, and that will always be 0. So we can see right away that the curl of this force is 0. That coupled with the fact that the force is dependent only on position tells us that this force, the 3D harmonic oscillator, is a conservative force. And if that's true, then there must be an associated potential. Right, so since F is conservative, there must be an associated potential. And that potential is related to the force in the following way. If I take minus the gradient of the potential, that potential only depends on position, I will get the force. Okay, so the question is, what is this potential? For this particular force, minus k, x, y, and z. Okay. Well, some information that we have is the following. We know, I'm going to come over here now, on the left-hand side. We know, okay, that the force in the x direction is minus kx, and that is equal to minus du dx. Okay. So that tells us that whatever this function u is, it has a partial derivative with respect to x that's kx. And you can repeat this for y and z. And you get the same result for z. All right. And you can show that a potential energy that is 1/2 k, and then inside x squared plus y squared plus z squared, when you take partials of that function with respect to x, y, and z, you'll get these terms, kx, ky, and kz. And that gives you an associated force that is the force of the 1D harmonic oscillator. How did we know to write this? Well, we know in one dimension, for a one-dimensional spring, the force is equal to minus kx, and the potential is 1/2 kx squared. And we just treat each of those three directions equivalently, including the z force, like so. And that allows us to expand to a potential in 3 dimensions. So this is kind of a, this shows that we have a restoring force along each of the 3 dimensions, but also no matter where you are, whether you're on the x, y, or z axis or anywhere in between, there's going to be a gradient of this potential that's pointing towards the origin. And that gives you a resulting force, which is minus k times the position vector, x, y, z. Okay, so with this example, it's a very brief example just to show how you calculate the curl of a force, and we did 2 cases. And we showed the connection, or reinforced the connection between the curl of a force being 0 and that force being conservative. And if the curl of the force is not 0, we definitely know that force is not conservative. Okay, so that's it for now, but until next time, take care and be well.